total of 4. And that's already me counted twice. That's included. All right, 5. All right, slowly people are getting here. Let's just see where we were last time. So we started talking about center manifolds. Center manifolds are a big part of the local puzzle in terms of what happens when you have a non-hyperbolic fixed point. Remember, if you have a hyperbolic fixed point, then locally near the origin, linearization is guaranteed to capture locally the dynamics for you, at least qualitatively, actually in a good sense also quantitatively, because you're close to the origin. So the transformation that takes you from the linear system to the nonlinear system is in fact a near identity coordinate transformation. So no surprises there. Interesting things start happening when you have a non-hyperbolic fixed point. A lot of the phenomena in nature that are kind of, you hear it a lot about things like tipping points or sudden unexpected changes and things like that. They tend to happen near non-hyperbolic equilibrium points because hyperbolic equilibrium points are robust. So there are small changes in the parameter space. They might deform, they move a little bit, they're not going to change. But these sudden changes are due to the fact, as we were talking about the steam engine, right? Things are working until things are okay, until they're not okay. So little changes in the parameters, in manufacturing and everything, it might change the modus operandi a bit, but there's a tipping point after which all hell breaks loose, or there's a different behavior. Now that sort of tipping point is, generally speaking, when you lose hyperbolicity for your equilibrium point, your fixed point. So they're crucially important. So what we're doing here is very important, trying to understand what happens near those fixed points that cease to be hyperbolic, right? What happens nearby? What is created? What is disappeared? So the first step in that direction is understand what to expect. And this is the basic picture that if you have such a fixed point, then invariably you must have a center subspace associated with it under linearization. That's where things kind of become neutrally stable. You will also have a stable subspace generally, sorry, I was pointing at the wrong thing. So once again, this is the unstable subspace. This is the stable subspace, and you have a non-empty center subspace. When you, in fact, and very often this is the case, you have no instabilities to begin with. So this is not even there, because then you would not really observe this point that much. Then it's very often only the interplay of the stable directions and the neutral stable directions that really determines what's going to happen. Now we know that in the stable directions, there's a surviving stable manifold attached to them, which is sort of driving nearby initial conditions towards the origin. So it's crucially important what happens along the surviving center manifold. The center manifold is not unique in general, and it's not as smooth as the original system, but it's known to exist. And it's tangent to the center subspace. That, however, is not unique, and we don't yet know. That didn't answer the question what actually happens there. So we started taking a closer look. So we just looked at an example, and remember, this example showed you that even the simplest examples, the center manifold is clearly not unique. There's infinitely many of them, and it's even a continuous family. All these curves are center manifolds, right? And I told you how you can immediately spot that they're not analytic, because no analytic, you could not have all these analytic functions having all the Taylor expansion from one side, the derivative 0 up to any order, and on the other side, at some point having non-zero derivatives. That wouldn't work for an analytic function, because then it would have to be identically 0 on the other side as well. It's only fun. In this example, it was interesting. It's going to be C infinity, but not analytic. So it will have a Taylor series expansion, which is even trivial, but it doesn't converge. So anyway, so in general, how do we determine the dynamics on the center manifold? We know it exists. We know it's not unique, but at least up to good order, the approximation should be the same, because the Taylor expansions of all these manifolds are the same. So what we introduced a new variable that contains now all the variables in the phase space. So it's n-dimensional. It has everything in it: stable, neutral, unstable, all directions in it. and I shifted conveniently the origin to the fixed point to the origin, right? So this is just the right-hand side of that system, and I took all the hyperbolic directions and I put them in their number, and the stable and unstable directions together. I call them D. So D is the number of hyperbolic directions, and C is the number of center directions. The two together add up to N. And the first step we did, we block diagonalized the linearization, which is a milder procedure than linearization. For two reasons, we didn't go for full linearization. The first reason is that you don't necessarily need to know the eigenvalues to carry this out. That's an advantage, because especially for large systems, that can be painful to calculate the eigenvalues accurately. But even more importantly, when the eigenvalues are complex, then linearization takes you out of your original real phase space, and you have to. You can make the matrix diagonal if it's a semi-simple. However, it will only be diagonal when you complexify the variables, and that's kind of sometimes that's very helpful, by the way. And we'll perhaps talk somewhat about that a little bit later on if I have time when we talk about normal forms. But generally speaking, it's not that great to multiply the dimension of your phase space. Start with complex variables and their conjugates. So instead, you just block diagonalize, which means that you separate you basically decouple the model at linear level. Namely, you pick a basis in EC. Mind you that these don't have to be actual eigenvectors of your linear part. It's just a basis that spans the center subspace, and also a basis that spans its say orthogonal complement. So a basis that spans the span of hyperbolic directions, and the basis that spans the center directions. And then we introduced a change of variables, linear change of variables, right? Z equals TC, which then will separate these two directions. And the way you perform that change of variables, you differentiate, as you always do. You differentiate both sides of these identities. What's beyond that, by the way? Why does all of a sudden space depend on time? Why can I differentiate space with respect to time in a perfectly normal Euclidean space? The answer is I can, but I always get 0. So why don't I get 0 here? Because I'm applying these to solutions of a differential equation across the board. So what I really mean here is that Z of t, the solutions of the differential equation, will be tc of t, the new coordinates. Only then am I allowed to say that, okay, so I want this coordinate change to be performed for all variables because I want to have the differential equation in the new set of variables. Therefore, I can differentiate like that. Okay, so that's what's in the background. We're just suppressing that in the notation. So all of a sudden, that's why Z dot is in fact the same Z dot that you had for the differential equation. And then C dot will be, and that's our objective, to express the OD in this set of variables, just T inverse Z dot, and then whenever so we take this Z dot, and wherever we see Z, we plug in TC, right? So this is in the first run, and then when I see Z, I plug in TC, and that gives me the T inverse M TC plus order C squared. And this is just a representation of M in this basis. M was the original Jacobian. And then in this basis, therefore, because that's the construct that I have, this is an invariant subspace. This is also an invariant subspace because it spans EC and it spans EU plus ES, right? Those are individually invariant subspaces for the linear dynamics. So then there will be no cross communication at the linear level among these directions. So you get a C by C block and a D by D block. If you pick these to be eigenvectors and you're in a real setting, so all eigenvalues are real, then you would in fact now have a diagonal matrix in both. But that's not needed, strictly speaking, for what I'm going to do. So this is where we were. And then let's just take stock what we have so far. If I now split this C variable, which is, mind you, n-dimensional, I split it into two variables, x and y, and x I take to align with these guys, with these directions. So first C component of C is just x, and the remaining D components of C I call y. That's what I did here. then because of the splitting at the linear level, I can rewrite the system like that. They're not going to be talking to each other at the linear level. It's this is where I have, this is what I have for A in M tilde. I didn't say that, so let me say that now. Let's just call this, you know, A, this matrix, and let's call this matrix B. And that's what I have here. And at the nonlinear level, I have order C squared, but there's no reason at all anymore why these two equations would decouple from each other. So they both depend on X and Y. And since I only did a linear change of coordinates on the CR functions, I have not changed their smoothness. So F and G are still CR. And both of them are order second order, meaning that they have terms like that big O X squared. These are norms of these variables in Y squared. So these the origin is still an equilibrium point after I add the nonlinear terms. This is where I was last time. Any questions? I need these recaps so that I remember where we were, right? You guys probably remember better than I did, especially if you watched the video just like an hour before the lecture, then you're more up to date, but I need to get up to speed. Okay, so where do we go from here? First, before I go anywhere, let's just see what happens in these coordinates. So the geometry in these coordinates, because I'm after the center manifold. So let's just see where I am. Have I made some progress in making that center manifold, which at a completely general position so far and shape? Have I made some progress in simplifying my life? So X and Y. Now X, because of my construct, remember, is now aligned with the center subspace, and Y is aligned with the rest. So X now is with the center subspace, and whichever way the stable and unstable subspace is related to the center subspace, maybe they were like this, because I have introduced coordinates on them, what I have done, I just made them to be two independent coordinate planes, okay? So not only did I align the center subspace with the X coordinates, which I'm gonna indicate now. So this is EC, but also the Y coordinate is now the span of these two subspaces, EC and EU. So that certainly makes it more convenient to think about things. So this is 0 there. And what I know is that the center center manifold, by everything I know that it's going to be tangent to this subspace, right? And after that, you know, who knows what will happen? I have no idea. This is the only constraint I have. So for all I know, this can be a pre-wired curve. And why would it not be, in fact? But all the things that I know about it make it somewhat regular near the origin, in fact, quite regular, right? Because it has to be tangent to EC. Now, I don't know, this is not the only way of being tangent. You could have another way, like you could have a cubic tangency, that's okay. But this is the most general case, which is quadratic tangency, which means that when I look at the graph of this function, and what's that function? That function is a mapping from of RC, the C-dimensional set of variables, which is X, into RD. In that set of coordinates, the center manifold attached to 0 is just the set of X, Y values from Rn such that Y is equal to H of X, right? So here's the thing. If important to understand that if I have a general center manifold, then I have no reason to assume that these Y variables that I have constructed locally to be aligning with stable and unstable directions, and the X variable, which is locally aligned with the neutral directions, I have no reason to expect that in this set of coordinates, the center manifold is a graph over the x variables. What's a graph? Well, a graph, again, is something that I'm showing here, which means that for any well-defined x value, you have a well-defined y value. Like here, you just give me x and I give you y. So immediately I have to, if you excuse me, restrict this to some neighborhood of Rn, right? Because see, if I move away, then I start folding back and say, look at this, right? At that point, for a given x value, which is here, I have two different y values. So the center manifold is no longer a graph of the x variable. So that's the local nature of this construct. But luckily, the minute you declare that you have a CR-1 curve, which is tangent to this line at the origin, then locally it must be a graph. Okay, and that you can actually beautifully work out, a solution to this equation, because essentially it's like rewriting this equation y equals h of x equals 0. Can I continue the solution of this equation from xy equals 0, 0, and then use the implicit function theorem, and then show that locally you can continue it. However, when there's a turning point like that, then you no longer have a unique subordination of y to x. But locally, when you have a quadratic tangency, you will have that, or even a cubic tangent. So it's really the tangency that enables me to do this, right? So this enables me at least to have a way of looking for the center manifold as a form of this graph, okay? In this set of coordinates. Now, if I had this other set of any other set of coordinates, suppose I did not do this initial change of variables, then for all I know, maybe these would be my initial coordinates in terms of the new coordinates, right? Maybe this is what I would work with. And it would be not clear at all that the center manifold would be a graph of one set of variables over the others, right? For instance, had I swapped the role of these, just imagine that this would be my domain over which I would want to construct the center manifold as a graph and therefore capture this curve. I would immediately fail, because if this is my domain, then that curve is not a graph over that domain, because no matter how close I am to the origin, I get two values. So it's not a unique function. So this is why we did this initial change of coordinates. So these are good coordinates to be in which this is for sure the center manifold is a graph. So this would be okay. And the conclusion is that in these coordinates, W center O is locally a CR-1 graph over X. I'll just try that, the X subspace. Okay, and the CR-1 just comes from the statement of the center manifold theorem. I cannot guarantee more in general, in the specific cases, perhaps. So what's the next step? Because this is nice, but I would actually like to get a handle on what happens on the center manifold. So far, I've just done a linear change of coordinates. Now here comes an important step that is true not just for center manifolds, but any invariant manifold calculation. Generally speaking, an invariant manifold is a surface in the phase space of a dynamical system, so that if you start on it, you stay on it. Why do we care about such surfaces? We care about such surfaces if they have an impact on others. Very often they say repel all trajectories or attract all trajectories. So for instance, you can have an attracting surface, an attractor. And then if you then identify what's happening on the attractor, as I mentioned many times, then asymptotically you can predict the fate of all your solutions. That's basically the mathematically exact way of reducing nonlinear dynamical systems to lower dimensional models. And this is the exact, not an approximation. So we care about them a lot, about invariant manifolds. And part 2 of this class spends a lot of time on general invariant manifolds. But the common trick when you go after them is you actually do use the invariance. So in what way can you use the invariant manifold even though you don't know what the manifold is? So use the invariance of the center manifold, even though we don't know what it is. So what does it mean, use the invariance? Well, it just means that for all solutions, if xt and yt as a solution, as a pair, okay, and I shouldn't, no, okay, I write this is the element of center manifold that C for all t, okay, because that's what it means. You start on it, you stay on it, okay. Then we can then what's true, since the at least, okay, this is always true, but at least while I'm looking at u, this means that the y of t must be enslaved to x of t through this relationship, right? Because if I'm on this curve, this is a multidimensional surface. As long as I'm on it, okay, then this must hold. So as long as xt, yt is close enough to the origin, so as a pair, they are also in U, okay? What goes wrong after that is not that they all of a sudden miraculously depart from a surface. What goes wrong after that is my representation, is that, you know, the largest maximal set will be probably, you know, somewhere here, that if I were really ambitious, then I could extend it, you know, to this neighborhood, and it would still be a graph, but not over that, okay? So why does that help? It helps because when you see anything like this, invariance condition, then you feel a natural urge after a while to do exactly what I did just 2 minutes ago, differentiate with respect to t. Because this is an identity, then it holds for any time. Everything is smooth in here, certainly the solution, certainly the function, at least CR minus 1. Why don't we differentiate? So differentiate with respect to t. If this was a star, then differentiate star with respect to time, okay? And what does that give to you? Well, on the one hand, I get y dot, and I'm just not going to write out the time for each and every value of time, but that's understood. And then I differentiate, then I have to do implicit differentiation, right? Or the chain rule rather. So that means h of x, and again, I'm suppressing now the argument, but what I really mean here is that I'm at a point on the manifold and the solution is running there. And then I have to multiply that by h of x, but I had to take the derivative of that. So that's Jacobian with respect to x and then multiplied by x dot. And now I use the fact that this x actually is a solution. Let's not forget that it solves the differential equation. So it's also a solution of the differential equation. So as a result of that, I can write that this is dh of x. And now I use the differential equation, x dot equals ax plus fx. And then instead of y, again, I'm using the fact that this is not true what I'm writing for any solution. This is not what I wrote here when I was talking about this operation. That was true for any solution of the differential equation because I was changing coordinates on the whole space. This is no longer true for every solution. It's only true if I'm also simultaneously not even just close, but I'm on this manifold, right? Otherwise, this enslavement relationship is not true. Let's just make sure that we don't mix this up. So I tend to use a different color usually. So let me use this star here. Okay, and that's just star there. Okay, but that, as long as I'm on the manifold, this is satisfied, but also the differential equation is satisfied. However, when I see y, I will just write h of x, because don't forget that all this thing is only valid when I'm on that invariant manifold. So on the one hand, on the other hand, I started out writing y dot, okay, and then I used this enslavement relationship. But as I said, this is also a solution, this x dy is a solution of the differential equation. So in order for me to figure out what y dot is, I can also go back to the y equation and exploit that. But wherever I see y, I would have to plug in h of x because I'm on the manifold. So look what I write then. I start from here, and whenever I see y, I plug in h of x. That brings me to b times, and now comes h of x. plus G times X H of X. Good. So why is this good? Because now I have two equal representations for the same object involving both equations. So when I then say that these two must be equal on the center manifold, that implies that I can take the right-hand side of these equations and equate them with each other. So I take the first one, DHF of X, right? Multiplying AX plus FX H of X. And that should be equal to B times H of X plus G X H of X. And the beauty of this, which I don't know who had this idea first, but it's pretty amazing, that if you look at this equation now, it doesn't depend on time anymore, and it doesn't depend on Y anymore. So although I kept saying that my arguments are only valid on the center manifold, in saying that, I also eliminated Y, and this equation is now only posed on this spatial domain X here. And on that spatial domain over which the center manifold is a graph, I don't have to care anymore if I'm on the center manifold or not, because I managed to essentially project the problem on, not even project, restrict, because projection is an approximation, you restrict the problem to finding a good parameterization for the manifold. So this is now for any X such that X, Y, for any X of X, Y is in U, okay? And also for any X, Y that's on the center manifold, but I don't have to worry about it, because as long as if I solve this equation for H of X, then I will simply say whenever I want to be on the center manifold, then I will compute the Y value from that relationship H of X. But I can independently work with an equation that only depends on X. Okay, that's the positive message. What's the negative message? There's no free lunch, so there's got to be something that's negative. And here's the thing to consider. If I thought that solving a nonlinear general ODE was a hard thing to do, which I thought because I'm trying to avoid solving it, I'm trying to make predictions instead of just solving it, then how about solving a nonlinear PDE? Because this is a partial differential equation. See, this unknown function H of X, so this is a nonlinear PDE. Okay, so basically H is mapping into our d-dimensional space, and it has C arguments. And even in the simplest case, when the center manifold is one-dimensional, well, then I get a, okay, granted, in that case, I have an ODE, and then RC is then C is the, like the time-like variable with respect to which I'm differentiating. But look at the complexity of that ODE with all the implicit dependence on H, right? So that doesn't seem to be any fun. And then when EC is two-dimensional, then truly this Jacobian is a 2x2. It's not 2x2 because it depends on how many other dimensions you have, but already has two different partial derivatives. Okay, here, and then all the rest depends non-linearly of H of X. Not only is that a problem because of what I have just described, but there's a bigger problem, in my opinion, because, hey, we could say, all right, then get a good PDE solver, solve the PDE. And that's a legitimate argument. PDE solvers are pretty advanced. But in order for you to solve a PDE, you need, of this kind, you need boundary conditions. And what do we know about the center manifold? Well, not much. The only thing we know about it is go through this point and tangent to it. So that gives us some idea of what it does here. But at some point, you have to cut it off and solve it on a finite domain. I don't even know how big that domain should be to begin with, but maybe I just fix one. What sort of boundary condition would I prescribe for the center manifold here and there? And mind you, this is a surface. To be honest, I have no idea. So there are more conceptual issues here in that case, not just the fact that I need to look for a good solver. It would require boundary conditions. So with the unknown boundary conditions. except that my and like I said, at the origin, even that is not a good, it's sort of a not really a boundary of the domain. That's in the middle of the domain. And that's just really information at one point. And you really, for a real boundary condition, you would have to look at the boundary of that whole domain, right? And prescribe what the center manifold looks like over that, but that's part of the question. We don't know that. Okay, so what can we do instead? Well, what comes to rescue is that, in fact, I'm very interested in just a good approximation, and really just sort of an approximation based at the origin. And if I really give up knowing exactly where my approximation breaks down, then I can just more focus on this part and try to solve this equation by Taylor expansion. So Taylor expand the unknown function at the origin. Okay. So for this one, I'll just say cannot be solved. Certainly not analytically. But I'll just add or numerically either, because there's this lack of information here. Okay, so what do you do instead? The idea was that Taylor expand. Let's call it double star. Near the origin. And let's just hope that we get somewhere with that. Right now, the origin is just described by x equals 0. Luckily, I reduced the dimension of the problem by passing to this equation. Okay, so how do I go about that? Well, first I need to clarify the Taylor expansion of what I'm looking for. And in fact, it's really the coefficients of h that I'm fishing for when I pass this to a Taylor expansion problem, right? If I say I don't want h as a function in general, but I want it in the form of a Taylor expansion, then what I'm really asking for is the coefficients of h in a multivariable Taylor expansion. Once I get those, I have a solution at least up to a given order. So how do I go about that? If I expand around 0, this is a multivariable Taylor expansion, then the first term is just a 0th order term, h at 0. Then I take the Jacobian of h at 0 and multiply it by my distance from the origin, which is just x, right? And then maybe I write out the next term, which is the second order term. So that will be the second derivative of h, which is not actually a Hessian in this case in general, because h is not scalar valued. But remember, h maps into the whole d-dimensional space of hyperbolic directions. So this is in fact a high order tensor in general. It's a 3 tensor, or 2, yeah, 3 tensor, right? Because if it's h is vector valued, then its Jacobian is already a 2 tensor represented by a 2-dimensional matrix with 2 dimensions, right? 2 directions. And then when you take one more derivative, then you think of it as a cube. If you want to think of it geometrically. So I just use this general vague tensor product notation appropriately. I think I use this, that's often used in the literature, that this is the appropriate contraction or operation when you're multiplying it by x twice. So it's bilinear, it's quadratic in x, and ultimately when you apply this 3 tensor to these x vectors, then the output has to be a vector. Okay, so the first of these, it contracts h down to a 2x2 matrix, if you will, and then this is just the 2x2 matrix applied to a vector, and it gives you a vector of the same dimension. Okay, and then I'll stop there, and this is the high order terms. If this looks mysterious, just think of passing to components of h. This is then a scalar valued function, and do a good old, multivariable Taylor expansion of that scalar valued function. This is a shorthand notation for what will arise when in invariant notation when you do it all at once for all components. Okay. Now, is it really this bad in general? Luckily, there are simplifications immediately, which all come from this geometry. One thing to note is that h goes through 0. And that means that what's the value of 0 at h at 0? Well, it's 0. So then this term is out. Okay, the other simplification is that h is tangent to this subspace, maybe quadratically, maybe cubically, but either way, it has a tangency. That means that its derivatives with respect to all these x, the derivative of h with respect to any x direction must be 0. As a result of that, luckily, that Jacobian also vanishes. So I still haven't said much about what comes next, but this is already a major simplification because a lot of the terms in this, the leading order terms, are 0. So basically, the way you can simplify your search or focus your search on x is that you just have to look for a general quadratic function, at least quadratic, in all these variables. Okay, and then you go as high in order as you need for accuracy. Okay, so seek the center manifold in this form. Remember that this is only possible after you have made this change of coordinates. Had we not made this change of coordinates, then there would be uncertainty whether this representation for h as a graph is valid or not in my current coordinate system A. B, that term would still be out because I'm going through the origin no matter what with that h, but this I could not cross out because, say, in this set of coordinates, right, h has just a finite slope here. So I would then have to store all those coefficients and look for them in a numerical computation. So it is bringing me savings to use these coordinates because in these coordinates, those terms are out. Okay. Now, before I do this on an example, because actually there's not much I can do without now getting specific and look at an example, I just want to point out where we're heading with this ultimately is that once we have determined this, so then really depends on the given problem. So at this point, we have to get our hands dirty and plug it in. But we can already anticipate that once we have that, what we really wanted to do in most cases we're interested in really what happens on the center manifold. And this gives us a way to get there because the dynamics on WCH 0, once you have some approximation to this, maybe quadratic, maybe cubic, maybe up to fifth order, depending on your need for accuracy, right? Because what we're doing is we're approximating this curve locally, right? With something like this. And depending on how close you want to get to it, you use higher and higher polynomial extensions. But assuming that you perform that extension according to your needs, once you have that expansion, you can reduce the dynamics to the center manifold. How would you do that? The center manifold is, once again, a graph over the x variable. That's the great thing about having an invariant manifold that's a graph over your favorite variable, that if you know the dynamics here, then you can lift it up and get the dynamics for y of t. So more specifically, look at this relationship that I derived here. Suppose I have some understanding of x of t, which is your sort of modeling variable in this reduction story. Then once you have h, you can lift it up to y of t. So what we say is y is enslaved to x of t. Okay, so that's the big advantage of working with these coordinates and with center manifolds. So again, the thing here is that y is enslaved to x along WC0, right? So that's just a remark there. Okay. So so if I know the time history of x on this portion of the center manifold, I don't have to worry about y because it's just given. I don't have to reconstruct the evolution of y separately. I just have to plug into this function, and that lifts me up to this curve, no question. So it's enough for the reduced dynamics on WC, not just to look at what happens in the x direction. What's happening in the x direction? I'm solving still the differential equation. So whatever I have in the x direction must be conforming to the differential equation, except that when I see y, I don't have to worry about y, I just plug in h of x. So that gives me f, x, h of x, and there you go. This is as exact as it gets when you want to do model reduction in these problems, right? It's just only a function of x. It involves no projection. It's a restriction. So what we call this the reduced dynamics. And what it is, I want to emphasize this term, which is restriction of the dynamics rather than projection. In a linear system, as we, I think, discussed a few times, you can understand the net evolution in the phase space by projecting onto invariant subspaces, handling them separately by linearity, and then solving them and then putting them again together. So projection is not a bad idea for linear systems. It can be a very bad idea for nonlinear systems because such a superposition relationship doesn't hold. But the nonlinear, although more painful but exact alternative of projection is a restriction. You actually look for invariant surfaces in the phase space. You invest in that. You then, once you know them, you restrict the dynamics to them. You can restrict the dynamics to invariant surfaces. You cannot restrict the dynamics to eigenspaces of a nonlinear system because they're no longer invariant once you add the nonlinearities. But the manifold is invariant. You just have to have a good parametrization of the manifold, like this x coordinate. You can work with the manifold, and if you know all the directions the manifold is attracting, then you have a great reduced order model. This is conceptually clear. Of course, how you do this in practice is another matter. And we're looking at now the simplest case in which this is technically doable. So what this, in fact, then achieves, I'd like to point that out, is model reduction. When is this a good reduced order model? Let's not forget about that. When originally the unstable subspace was the empty set. Because then, let's just go back to this picture, then in the phase space, the only remaining directions are stable directions. So you will actually be running towards this manifold. Whichever way is not that important, but it's then ultimately it's enough to understand what happens here, especially, I mean, when you're near the origin and you know really what the manifold does. Okay, so that then leads to model reduction. And it's the dimension from n dimensions to c dimensions, right? And that can be significant. It can be, in fact, n can be, this extends this idea of center manifolds to partial differential equations, infinite dimensional ODEs. Then you have infinite dimensions. And if the center directions only involve, say, 2 dimensions, which is often the case because it's not that your whole spectrum will be entering the negative part of the complex plane with the eigenvalues all at once, but typically 1 or 2 passes at once. And then right at passage, you have a center manifold, which is 1 or 2 dimensional. And then you have the opportunity to reduce to that because all the remaining directions are still on the other side of the complex plane, right? In the safe side, I don't know if I'm pointing in the right direction here, but in this case, you know what instead of hand waving, I could actually draw a picture, right? So this is especially effective when you have the real parts of lambda I and the imaginary part of lambda I, okay? And we're looking at this case, right? And say you have been varying your parameters and say a pair of eigenvalues is just crossing the complex plane. I'm sorry, the imaginary axis, say in this direction, but all the others, let's say here, and you can have a whole bunch of them, right? A lot. So imagine you have discretized, say, the Navier-Stokes equations, your solver will always be finite dimensional. So you're going to have a what are, you know, hundreds of thousands, millions of eigenvalues still here, and one pair is right at criticality, they are crossing right here, okay? And that instance, this gives you an opportunity, this, to reduce your very high dimensional model to two-dimensional surface locally, okay? And understand what happens right there, the loss of stability, because that's where interesting things, non-trivial behavior tends to be born. Now, how do you do this? Are there any questions on the general philosophy or procedure? Because there's an example I wanted to show you in more detail, but before that, if there's anything unclear. Nothing? Okay, and let's look at the example, maybe then. So where is the example? So again, instead of rewriting this, I'll just walk you through this, and then I'll copy it into my notes. Okay, so here's the example that I wanted to look at. This is a two-dimensional ODE. So, you know, you're not going to have a dramatic reduction, but you already have some opportunity for reduction here as well. It's linear. No, I'm sorry, it's non-linear. This is the only linear term. And clearly the equilibrium at the origin is an equilibrium point. I'm going to focus on that. So x equals 0, y equals 0 is an equilibrium point. There's only one parameter here, which is alpha. It's a real number. So what's the first step to understand the dynamics of this system? Always look for equilibria. So when x is equal to 0, then this part is here 0, that's also 0. So the only equilibrium is then at y equals 0. When y equals 0, in the first one, so the first equation vanishes the right-hand side because y equals 0, then not only is this term out, but that term is out. So the only way for me to have 0 for the right-hand side of the second equation as well is that this term has to vanish. So x is equal to 0 as well. Long story short, the only equilibrium point in the system is x equals 0, y equals 0. So I linearize there. So when I linearize there, what do? So this is like our proverbial z dot equals fz equation. Remember that is what we started out with. And in this case, z is x and y. So I linearize there, which means I take the Jacobian. So I need to look at the first equation. I take the x derivative at 0, which will be just y. So when I evaluate that at 0, it's 0. And the y derivative is also 0 at the origin. So I get 0, 0 here. When I go for the second equation, and I take the x derivative and the y derivative, again at 0, the x derivative vanishes, but the y derivative at 0, because after I differentiate with respect to y, I get -1 here, the y derivative will be -1. Good, so that will be my m. Remember that m here? Let me scroll momentarily back. Well, I can do it here as well, but this is not what I have just written. This is what I have established here before I do anything. And then I said the recipes define a transformation that block diagonalizes your form. Now, generally, that's how I would proceed, except that this example was so simple that I am already in a block diagonal form. Why? Because the off-diagonal elements are both 0. So I didn't have to do any extra work. In fact, what this tells me is that the x equals 0 direction is aligned with the center subspace. That's why I have the 0 eigenvalue. And the y, not x equals 0, the x-axis is aligned with the center subspace. And the y-axis is aligned with the y. Well, sure, that's always the case. The y-axis is aligned with the stable direction where you have decay. Okay, so what the linear dynamics does is this. So in this, you have a center direction corresponding to a 0 eigenvalue. There's for the linear system. So this is here the linearized dynamics. So the linearized dynamics is such that I have no motion in this direction, a bunch of fixed points. And it's basically the linear system that, what's the linear system from this? It's x dot equals 0, y dot equals minus y, right? We've seen that system before. So what that does is no motion in the x direction. And when I'm on the y equals 0 axis, no motion in the y direction either. It's a bunch of fixed points in the y direction always as exponential decay. We've seen this example before. The unstable subspace, therefore, is the empty set. That's why I wrote that the unstable subspace has 0 dimension. In fact, it's empty. And the stable subspace has dimension 1, it's this one. The center subspace also has dimension 1. Okay. So the question with this is a non-hyperbolic fixed point, as you see. Generally speaking, the picture you see here will not carry over to the nonlinear system. The question is what will carry over? That's what the center manifold analysis is for. Only thing I know at this point is that there will be a stable manifold which somehow continues this line here, and there will be a center manifold, who knows what shape, maybe this, maybe that, who knows, but it has to go through this point and it has to be tangent to that center subspace. What's our procedure for finding the center manifold? We had a general conclusion, that it's a quadratic function over the center type variables. The center type variable x is just one dimensional here, right? So h is a quadratic function plus higher order, but it starts at quadratic of x, which is one dimensional. So a Taylor expansion for h would be a times x squared, b times x cubed, c times x to the fourth, and so on. And I can go up to, and this is legitimate, up to any order r minus 1, where the right-hand side, this r is the smoothness of the right-hand side. Now the right-hand side is c infinity here, even analytic. So my infinity minus 1 is still infinity. So I could go on with this up to any order of precision that I want. But here I just want a leading order approximation. Generally speaking, doesn't converge, this approximation, as surprising as it may sound. So even though I can venture to calculate individual coefficients, what I cannot do is, in principle, calculate all of them and sum this Taylor expansion, because generally speaking, it will not converge. It only converges if the center manifold is unique, then it gives you a convergent expansion. So interestingly, you can calculate all coefficients, but generally speaking, this is a divergent expansion. Even if it's a divergent expansion, when you're close to the origin, this statement is true, that the way to read this is that the difference, it's not what we sometimes, for analytic functions, we say that I'm writing down, the first few terms of a convergent Taylor series expansion, and the difference between this and the converged full expansion is this. No, here, what this means is that the manifold, at least one of the manifolds I can single out and talk about, if I write down this expansion for it, then the error of approximation for that particular manifold will be order x to the fifth. But there's infinitely many other manifolds that are, in fact, in this order, indistinguishable in terms of their expansion from that manifold. And for them, it's also x to the fifth. So this is basically the error between what I'm writing here and the manifold, rather than the converged Taylor series, because it generally doesn't converge. That would imply that you have a unique manifold, which we'll see actually in the end. But do we have a chance to have a unique manifold? So use the invariance. So you either keep this in mind, which I don't recommend, this equation that I just derived, because the way I would reproduce it each and every time is precisely what I've just done here. Write down the invariance condition differentiated, okay? So either you memorize it or you actually each and every time you just to remind. Obviously, when you code it up, then this is what you code up, right? But if you just need to reproduce it in a calculation, then you just start from scratch. Write this down, this enslavement relationship, differentiate it in time, and plug in what you need for x and x dot and y dot, and you get this. Except that it's then expedient to do already that calculation using the expansion for h, rather than deriving the PDE and then expand. So one can do that simultaneously. How? So again, y is equal to h of x, right? On the center manifold. So y dot is equal to grad h times x dot. So just use the expansion of h already here And in every other occurrence, when you work these out, just use the expansions of the functions evolved. Luckily, you don't need to expand the right-hand side because that's already expanded. It's a polynomial. And very often that's the case with physical models. We tend to use polynomials for physical modeling. So that is certainly a doable way of proceeding. So y dot equals h prime of x dot. Since x is a one-dimensional variable, then instead of this more complicated gradient notation, I just used h prime because it's really just a scalar variable. So h prime x, I can actually execute given my ansatz for h. Okay, so I can actually go ahead and do that differentiation. This is how I get 2ax from ax squared. This is how I get 3bx squared from this term. And this is how I get 4x cubed from that term. The rest I don't know, but I know that if I differentiate them, then I get fourth order terms. And I just hope to get away with the leading order calculation, so I close here. Then I need to deal with x dot. X dot is xy. That's already a Taylor expansion of the right-hand side. If you had anything else here, sine or tangent and everything, and you're working here x equals 0, you would first then have to Taylor expand that, right? But this is already Taylor expanded, so that I don't have to carry that out. So you would have to Taylor expand it, and then whenever you see y, plug in for y also the Taylor expansion of h, right? So basically you're plugging a Taylor expansion into a Taylor expansion. But that's already performed here. So when I write up the right-hand side, I have an x here, which I just write down. And whenever I see y, I use h of x. That's right here. So that's why I have written this is just y equals h of x, right? So I took this form of h of x and plugged it in for y. So this is the one way of writing directly from the chain rule what y dot is on the center manifold. The other way of writing it, this was the second step that I used in deriving that nonlinear PDE, go directly for the equation. So you write that y dot equals minus y. So y dot equals minus h of x, because remember all this invariance means that you're on the manifold. So on the manifold y is h of x. And then you have alpha x squared. So for minus h of x, again, I'm trying to get away with as little work as possible, but I do want to account for these three terms, not many others. So what I've already done here, I said when I plug in minus h of x, then at second order, that will be minus h of x. Well, where's my h of x? It gives me a minus alpha, and I had a plus alpha x squared here, so I grouped them together already here. Excuse me. And then this gives me no cubic or any higher order contributions, so I can just take all the minus h of x terms and write them out here. So bx cubed goes into minus bx cubed, and cx to the fourth goes here, and then I still have the higher order terms here. So what I need to do is the same what I did when I derived that nonlinear PDE. I have to equate this with that. Same procedure, right? It's just a little bit simpler this way because you don't have to remember and term by term copy that PDE. And the only difference is that I'm being here a bit street smart, is because I don't need to write the PDE and then Taylor expand, but I'm working with the Taylor expanded version of the functions involved. Excuse me. I had some water here, but I don't see it. Oh yeah, if you excuse me for 1 second. Well, there wasn't much in it, but a little bit. I forgot to fill it up. Okay, so where we are now is that these are the two different representations that led me to a PDE. So let's just compare them. Let's just equate them. Now, because I have Taylor expanded forms for the left-hand side and the right-hand side of the PDE, I can just say these have to be equal for all values of x, which is only possible if the polynomial on the right-hand side is equal to the polynomial of the left-hand side. So term by term, I start equating them. On the right-hand side, I have a quadratic term, and there's nothing to balance that on the left-hand side. So again, I'm equating these two, right? When I talk about right-hand side, this is this, left-hand side is that. Now I have a quadratic term here, and if you start taking stock here, the lowest order term in the left-hand side will be when you multiply 2ax with x and then x squared. So the lowest order term has degree 1 to 4. So you're starting here with a polynomial which is at least 4th order. And on the right-hand side, you have a polynomial which is quadratic. How could that be? Well, no way. So the only way is that, no, there is a way. I can make this term vanish. I can demand that it vanishes because otherwise it doesn't match. Left-hand side. Can I impose that? Luckily, yes, because in fact, this A was anybody's guess initially. Alpha, I knew that's a model parameter. So when I say this is 0, and it has to be 0, otherwise I cannot balance the two sides with each other. So when I compare terms at order x squared, the only way for this equation to hold is A equals alpha. Right. That's great because A was unknown. That's why I'm doing the whole thing, to get some information about this. What about x cubed? Again, I have x cubed on this side, but remember on the left-hand side, the lowest order term has 1 to 4th order. Excuse me. So the only way this can hold is, again, that term, that coefficient on the right-hand side must vanish. So B is 0. And that's out. So this is also out, but that gave me meaningful information. Well, this is also meaningful information that in this expansion that's 0, but I wanted at least up to quintic order. Can I get some information about C? Well, it seems yes, because on the right-hand side, I have minus C as a coefficient, and on the left-hand side, now I am starting to get something, because the lowest order term, which is coming from the product of these three, is actually 2a squared. So that has to keep balance with the minus C. So 2a squared must be minus C. So I have two equations, well, three. B is 0, A is alpha, and 2a squared equals minus C. So note that luckily, this is a solvable system of equations because it is linear from the unknowns. Linear for A, linear for B, and linear for C. And this happens to be generally the case, luckily. So looking for the center manifold, generally speaking, leads you in this fashion to a solution of a linear system of algebraic equations. Okay, that's the beauty of it. So when you properly write it up and code it up, in the end, you just have to solve a linear algebraic system of equations, always. Okay? That's pretty neat. One doesn't have to solve a nonlinear PDE or doesn't have to look for it numerically. So when I plug these in, then h of x becomes alpha times x squared, right? And then the b term is missing. So the next term is really coming from here. So the next non-zero term is minus 2 alpha squared x fourth. And this is then the shape of the center manifold at leading order. And I could go on now. I could now throw in more unknowns here. Then they would keep appearing here. And one by one, I would be able to solve these equations because not only are they linear, but it's more than that. The way they are set up, generally speaking, and when I solve the lower order equations, then I can go for the higher ones. So there's no crazy coupling. I can actually do this recursively. That's the beauty of it, right? So I can really start in a system of equations. The matrix, coefficient matrix is such that I can just proceed in one direction. The higher order terms always depend only on the lower order terms that are already known. You wouldn't know that from this example because here the linear system of equations, they fully decouple. That's not always going to be the case. More complicated examples, but nevertheless, you will be able to start from the lower order, second order terms, and once you know them, go for the third one, and so on. And for the remaining variables, it will always be linear. So this is the shape of the center manifold, and it does depend on alpha. And see, depending on your system parameters, the shape can change and will change. I mean, most obviously, it will change the shape quite a bit when you change the sign of alpha. So there's two main cases, but before that, even before I don't have to go for the shape, the dynamics on WC, your reduced order model, for which you have a good case for, because there's no unstable direction, only stable. And remember when I told you when the remaining directions are all stable, then what's happening on the center manifold is ultimately what's governing your dynamics. So this is it. I'll get to that in a second, but the way to obtain reduced dynamics was, see, remember this equation here? Just go for the x differential equation, and whenever you see y, you will only see it in the nonlinearities. If you did block diagonalization, just plug in the approximation or h of x, and this is your reduced order model. So let's just do that here. X dot equals xy, that was the x equation. So whenever I see y, I plug in the shape of the manifold. That was right here. I can factor out x squared from this. And even alpha I can factor out. So when I factor out alpha times x squared multiplying x, then I get alpha times x cubed, and this was the rest. And I know even then the error of the approximation, that's the beauty of it, as long as I'm close to the origin, close enough, so to speak. That's the vague point here, is, you know, how close I need to be that, but this is always the, you can then say, all right, I can refine this approximation. I don't have to live with x to the 6 if I don't like it. I can just look for a high order approximation to begin with, and then I get more terms, and I can refine this further. So this is always the reduced model, and it doesn't get any better than this. This is mathematically exact, and once you know the x dynamics, the dynamics of this ODE, which is already nonlinear, but it's one-dimensional, then you can lift that dynamics up to the y variable. Let's look at the case when alpha is bigger than 0. So when alpha is bigger than 0, let's look at first what that means for the shape of the center manifold. This term will be then, and giving you an upside down parabola when alpha is less than 0, right? This is what I started with. No, okay, then alpha bigger than 0. And it's just a normal parabola. And this will be a fourth order parabola, but upside down, because 2 alpha squared is always positive, so you have a negative here. So basically, near the origin, you will look like this, but as you start moving away from the origin, of course, the fourth order term will overpower the second order term, become dominant. So it will then turn the whole graph back, and it will start going down, okay? But at any point, it will be symmetric, because you only have even order terms at this level of approximation. So when you put that together, then this is the shape of your center manifold, so the actual at this level of approximation. So I'm not keeping the high order terms, only I'm cutting off here. And then this is the reduced dynamics on the center manifold. If alpha, I can get into that later. Let's see, alpha is positive, right? I'll go into that later, then the dynamics. So let's just first worry about the shape of the center manifold, okay? And this is the first order shape of the center manifold. Now, somewhere in this picture, I also must have a stable manifold, because I had a stable subspace. Now that is a peculiar feature of this simple example, that the stable manifold actually survives as the stable subspace, that same line. How can I see that? Generally speaking, you're not going to have that in the general model. It will be something like this. And you can look for it, by the way, in the exact same way as you look for the center manifold, but it would have to be an invariance equation, an expansion formulated over this direction rather than this direction. And for that one, you can fully expect a unique solution, unlike for the center manifold. But the idea is exactly the same. It's just that you will have to write it down as a graph over the red direction. Now, how do I know that in this problem, it actually survives as the line? Well, that, like I said, that's generally not the case, but the equations are very simple here. See, x equals 0, which was this line, is an invariant line no matter what. Because if I plug in x equals 0, doesn't matter where I am with y, x equals 0 stays x equals 0. So how do I see that? Here's the x equation that would describe if it changed, but then I plug in x equals y, x equals 0, then it doesn't matter what y is, x just stays 0. So that means that x equals 0, which is this line, is an invariant line for the ODE. You can say, wait a second, maybe for y, that's the case. Well, let's try it. I plug in y equals 0 momentarily, and that this term is out. However, there's that term. And unless I'm right at the equilibrium point, this term is non-zero and hence will introduce a change in y, right? So the y equals 0 axis is not invariant. The x equals 0 axis is invariant in general. And on the y equals 0 line, it's only the origin that stays put. So that is not, this line is no more invariant, this center subspace. Nevertheless, in the usual projection philosophy that people apply for model reduction, that would not stop people from projecting the equation down to this line, as if it was invariant, right? So they would take the y equation and project it down to y equals 0. That's the way to do projection-based model reduction, right? So then this would then lead to y dot equals ax squared. Is that the real dynamics? This would be projection-based, and it's as clean as it gets, right? Because you would set y equals 0. That would be the best bet for the reduced order model. Well, not quite, because the real dynamics is that, even at leading order, right? So this would actually give you false information. Let's get to the dynamics a little bit later. But one thing I can already see is that the true stability type of the origin restricted to this curve, because in this direction, there was no question what happened. The big unknown was what happens here. When I go ahead and linearize this equation at the origin, then I still have a problem because the linearization is still degenerate. That hasn't changed. So you might ask, why am I better off now after all these calculations? The linearization is still inconclusive. And you're absolutely right. But now I have a one-dimensional system. And a one-dimensional system, I'm perfectly okay doing analysis without linearization. I can, in fact, globally figure out what the dynamics is. Remember, when you have a one-dimensional system, x dot equals f of x, you just plot the right-hand side. This was x, this was f, so to speak. And then whenever it's positive, you put a positive there, negative, positive. This is what we did. These were then fixed points. And then therefore you will be growing here, you will be decaying there, you will be growing there. So you get the one-dimensional phase portrait just by plugging the right-hand side. Here, there's an alternative argument that when x is very small, then this term is tiny compared to 1. So when I'm looking at really what happens very close to the origin, then I can take this to be approximately 1. What I'm doing now is basically, I'm doing this in my head, but I'm approximating this graph function near the origin without drawing it, okay? So it's just roughly 1. So it's the shape of the function is locally governed by this. So locally, that right-hand side locally will look something like that. It's going to be a cubic function. And then, of course, it's going to be different afterwards, but locally for alpha bigger than 0, it's a cubic function. So I will have a plus here, and I have a minus here. So my local dynamics is growing in this direction and it's decaying in that direction. The upshot is, therefore, that the origin is unstable. And that's how I concluded it from here. And again, if I just go by linearization, then I would not be able to conclude that because the full two-dimensional system is coupled, it's hard to analyze. But because of my reduced order model is just one-dimensional, whose dynamics I can even figure out without ever even solving it, right? That enabled me to decide that the origin is non-linearly unstable. So in effect, what it is, it's a weak saddle because you have exponential decay here, and here you don't have exponential growth because it's coming from nonlinear terms. When you work that out, it turns out it's algebraic growth in T. So it's slower, but it nevertheless is growth. So it's taking you out from a neighborhood of the origins. Origin is unstable. What happens when alpha is less than 0? When alpha is less than 0, that turns this quadratic parabola upside down in the approximation for the center manifold. The second term is the same. So what's going to happen is that at the origin, you have an upside down parabola, and it never turns back, but it would go like this, but it's even gaining strength in this direction. The downward trend just continues when you add the fourth order terms, right? So the shape then will be more like this. And again, it hasn't, the fact that this is a surviving stable manifold, which used to be a stable subspace, that hasn't changed, right? It's the same argument. However, now when I go through the moves here and I want to understand what the dynamics are like along this curve, then again, it's still true that this term here is roughly 1. Therefore, the leading order dynamics will be governed by alpha x cubed, except that now alpha is less than 0. So my little cartoon will be just the opposite. This is minus x cubed locally, right? This is x and this is f for the reduced dynamics. So it's going to be positive here and it's going to be negative there. So I have decay here and I have growth there. So that means stability. That's why I have drawn these arrows here. So yet another very useful conclusion is that the origin now is no longer a saddle, but it has turned into a node, and it's asymptotically stable with a fast exponential decay in this direction and a slower algebraic decay in this direction, but nevertheless, that's decay as well. So the interesting thing also in this case is that by here I created a saddle, and therefore, then strictly speaking, I introduced a new weakly unstable direction. If you define the unstable manifold more generally, and you just say, is the set of points that in backward time under the flow map go to the origin, then this is an unstable manifold. It's not going to grow to correspond to exponential growth. It has no signature in the linearization, but it is created by the nonlinearity. So technically, this is now an unstable manifold born out of nothing. Weak in terms of repulsion, not exponential, but persistent, algebraic, at least near the origin. After that, it may pick up speed. So it is an unstable manifold then. What's happening here is that instead of creating something new, you're essentially enlarging the dimension of the stable manifold. Because all of a sudden, in a neighborhood of the origin, everything just converges here, right? Because you're decaying down to this manifold, and then along the manifold you're going. So you have what we often call here now in this context, the fast stable manifold component, and this will be then called the slow stable manifold. But technically, the actual stable manifold is a whole open neighborhood of the origin, which you can then even track in backward time and see how large it is, right? So this essentially makes the de facto stable manifold two-dimensional, but it has a weak direction. And again, you see how the model reduction principle works, that everything else decays exponentially fast, and then you have this creeping motion coming in. Same here. Things decay exponentially fast, but then the instability takes you away. Here, it takes you in. Okay. Now, one other thing, so this feels like a success story, certainly to me, but there's one inconvenient bit that I also have to mention. That this is still just a truncated approximation. So it will be perfect near the origin, because these terms, if you're close to the origin, they're absolutely dominated by the terms that I have kept, okay? So both the shape of the center manifold and the actual dynamics, very close to the origin, you can absolutely trust, because there will be orders of magnitude differences between what I'm adding here and the leading order terms. Okay, huge. I mean, this x is 10 to the minus whatever 3. I'm close enough. Then x to the 6. This 10 to the minus 18. Okay, this wasn't 10 to the minus 3, but this 10 to the minus 9. And it's 10 to minus 18. No question, right? This will dominate for a while. Once you get out of that comfort zone, of course, things might change. Now, that's precisely the thing here, that this the reduced order model will be more and more accurate in time. It will self-correct any error that it may have upon truncation, because the relative importance of these terms is actually going down in compared to the leading order terms. That will be better and better. Whereas this one with the instability, it correctly predicts the instability, but I have to be prepared that it might at some point predict things that are not there. Why? Because once x is increasing, at some point, the order of magnitude of this term and that term will be very comparable. And who knows, maybe this is 2, this alpha, and maybe, who knows, maybe the first leading order term here has a coefficient which is 20,000 to begin with, right? So pretty soon it will become very comparable. So when the two are comparable, then I actually have no longer a bona fide justification for ignoring it, because it's just as important as this term. And you see that here in this problem, not in this one, but as you start following the trajectories, and this term, you know, gains relative to that, because once your x is no longer tiny, then who's to say that the leading order term dominates? And you can see that actually here, because the order, if I truncated at order 5, and I didn't have any order 5. The order 5 term had 0 coefficient, but I can say 0 times order 5. So technically, this is valid up to order 5. I'm sorry, that this is already order 5. I mix it up. No, so this is an order 5 truncation, and you would think that's pretty good, and it is good for a number of things. But here comes the surprise. Now look at this dynamical system. When alpha is positive, it actually has 2 fixed points. So it has 1 fixed point at the origin, but the right-hand side of this reduced model, it also vanishes when x squared equals 1 over 2 alpha. And that equation has a solution when alpha is positive. It has no solution when alpha is negative, but it has a solution when alpha is positive. And lo and behold, since it's a quadratic equation, it gives you 2 roots. So it will actually give you 2 roots, so equilibrium fixed points. You have x equals 0, and then you have x, this is x1, and then you have x2, 3 equals plus minus 1 over 2 alpha square root, except that the square root is, square root, right? And those happen to be right here. Now you could say, great, so then I have predicted some non-trivial state in my reduced order model, except that those should be, if they're correct predictions, they should be solutions of the differential equation too. And you plug them in, remember what we concluded, don't even have to plug in. This has a unique fixed point. The only fixed point the ODE has is at 0. So your reduced order model, actually, if you take it too seriously and you don't higher order, and you started extending it into domains where you have no a priori reason to ignore higher order terms, it can give you completely misleading information in those domains, right? So these are the 2 fixed points that it would incorrectly predict. And the reason is that they're, like I said in the notes, they're no longer tiny. They're no longer guaranteed to be small. So the truncation in that regime is not justified. Does it mean that the whole technique is wrong? No, it means 2 things. First of all, you can certainly trust it close to the origin, and you can certainly trust the approach for evaluating the stability type of the origin, because right at the origin, anywhere you cut this, essentially, this one would be infinitely larger than what you have neglected. Okay, and that already plays out here. I could have done a cubic truncation and work with this, and already that would have given me the right result, even though there are 5th order terms that I'm not considering. And the reason is that, you know, order x cubed in norm divided by order 5th, right? That goes to, well, maybe I should look at it blows up when x goes to infinity, goes to 0. So that means that this is that the ratio between the two is that like, so when x goes to, this blows up. So the right way of doing it is order to x to the 5th, order x to the cubed, which goes to 0 when x goes to 0. So the significance of this relative to that is going to 0. So it's like not even there. Whenever I cut it, But when I move away, I'm now in a finite distance. This is a finite distance. To alpha was a finite parameter. Then I have no a priori reason to say that I can ignore the other one. So there's something to be aware of. The other question that I wanted to get to, and maybe I finish here, is any questions, by the way, about this calculation? The other question is that I've been, emphasizing all the way that modern dynamical systems is interested in robust things. That's why we're looking at hyperbolic fixed points to begin with. But then, as you change parameters in a system, sooner or later, you will also go into non-hyperbolic fixed points. And then we're interested in what that creates later on. But fundamentally, we've been interested in robust concepts. So therefore, are these calculations that I'm performing here in detail for the non-hyperbolic fixed point, because this is all done in the non-hyperbolic fixed point, are they robust? Is this calculation relevant under parameter changes? In other words, are center manifolds robust themselves? Because remember, I really have tied them to non-hyperbolic fixed points. And non-hyperbolic fixed points as such, they tend to be non-robust unless you have a very degenerate family of models, which you should then probably change because the parameter variation keeps you in that degenerate state. So if I now add a small perturbation to this example, which is just this part of the example is just the example that I've analyzed, and I'm adding a small, even linear perturbation to it. And then I go again by the book and I linearize. See, that hasn't even changed the equilibrium because x equals 0 is still an equilibrium point. Now I linearize, so all of a sudden my Jacobian, the right-hand side will be, epsilon x, Jacobian applied to xy, and minus y. So the difference is this term. This used to be 0. Now it's this. What's happening now? Well, what's happening now is that if I do a stability analysis, then in the x direction, I have an instability when epsilon is bigger than 0, right? If epsilon is less than 0, which some consider to be a joke in mathematics because epsilon is always bigger than or equal to 0, but this is just a parameter, it could be, then what I have is this. When epsilon is larger than 0, then the opposite. In the y direction, I always have that. So the conclusion is that if epsilon is non-zero, so this is a true perturbation, then I either turn this into a node or I turn it into a saddle. In either case, there's no center direction anymore. So the whole theory, you could argue, goes through the window. So why would we do it? Because I always encourage you to have robust models, and apparently the center manifold is not robust. And that's an absolutely, that's true. So the question is anything there still? And the answer is yes. And the good thing is, and I'll get to that tomorrow, I don't want to do it, that all this work wasn't done for nothing, because it turns out that with a trick, you can take that center manifold and continue that even as now a different manifold for small values of epsilon. You will still be able to continue that as an invariant manifold without really having to introduce a new theory for this, because it turns out that the very same center manifold theory, when you extend it in an appropriate sense, guarantees it for you that you can continue it. Okay, so that everything we've done so far wasn't done in vain, but this is something to realize that strictly speaking, classic center manifolds only exist at the point of failure of hyperbolicity. When you perturb away from that, you move away, you have to add something, a different formulation or a trick to be able to save what you have computed. And that's what I'm going to be doing tomorrow. I don't want to get into that now. Any questions? No questions, then I'll see you tomorrow. Have a good evening.